Can you see my screen?
Yes.
Thank you. Okay, so first of all, I'd like to thank the organizers for inviting me to this conference and for organizing this excellent conference. My talk today will be on D-instanton contributions to string amplitudes. So I'll begin by giving some motivation. So we know that string perturbation theory can, in principle, generate perturbative contribution to string amplitudes to any given order in string coupling. And you can imagine the resummation of this amplitude can give the contribution from path integral over the steepest descent contour, or more generally left phase thimble associated with the perturbative saddle point. Now, if we can carry out a similar analysis for other saddle points, then that could generate the contribution from the left side thimbles associated with these other saddle points. And if we could do this for every saddle point, then by taking appropriate weighted union of these contributions, we may be able to give a non-perturbative definition of string theory, okay, at least in principle. So our goal today will be to understand the perturbative contribution from a class of saddle points. And those are D-instantons, or more generally, Euclidean D-branes wrapped on compact cycles. The second motivation comes from more practical reasoning that D-instanton contributions play an important role in studying many aspects of string phenomenology. This includes moduli stabilization via KKLT or LVS scenario. And in a given compactification, the computation of echo couplings or gauge field kinetic terms often depend on D-instanton corrections. But before we get into these general computations, we should test this procedure on examples where the results are known from various conjecture duality relations. So in particular, one example that has been studied in detail and it has been discussed earlier is two-dimensional string theory. The topic of today's talk will be 10-dimensional type 2B string theory. But you can also consider type 3 or type 2B string theory compactive or Calabi-Yau manifolds. Okay, this is some work in progress with Sergei Alexandrov and Bogdan Stefansky. So let me describe the issues first. The dynamics of D-instantons, including Euclidean D-branes on compact cycles, is described by open strings with ends that are stuck on the D-instanton. And these open strings do not carry any continuous momentum. Therefore, the infrared divergences associated with the zero modes cannot be treated by analytic continuation, okay, which is the standard way we treat divergences in string theory. And in the worldsheet description, these divergences will show up as divergences from the boundaries of the moduli spaces of Riemann surfaces associated with open string regeneration, okay, because these are zero modes associated with open string states. So the strategy that has been successful in earlier work is to represent the worldsheet contribution as coming from sum over Feynman diagrams of string field theory. Then we explicitly remove the zero mode contributions from the internal propagators. And finally, we carry out the integral over the zero modes at the end. And this generates unambiguous divergence-free results for D-instanton amplitudes. However, if we want to compute the overall normalization, okay, which is associated with one loop determinant of open string fields in the instanton background, that requires a somewhat different approach. And this is going to be the subject of today's talk. So we'll illustrate this procedure for a particular class of problems. And these today will involve D-instanton contribution to type 2B string theory amplitudes in 10 dimensions. But I should emphasize that the method that I'll describe is quite general, and it applies to any Euclidean D-brane in any string theory. So let me now describe the problem that we want to tackle, okay, the specific problem. So we considered 4 graviton scattering amplitude in type 2B string theory. At tree level, this scattering amplitude is given by the supergravity result and an additional R2D4 contact interaction. Okay, this was worked out by Gross and Witten in the 80s. And this is the form of the tree level amplitude for these 4 graviton scattering. I've written the amplitude in the alpha prime equal to 1 unit. So this is the unit that I'll be using throughout. Kappa square, okay, is related to Newton's constant, but more importantly, it's related to the string coupling GS by this formula. And in my convention, the string coupling GS will be chosen in such a way that the D-instanton tension, the D-string tension is 1 over 2 pi GS. So because in the alpha prime equal to 1 unit, the fundamental string tension is 1 over 2 pi, defined this way, the S duality, for example, has simple action as GS to 1 over GS. So that's why you choose the GS in this particular way. The Kc here is a kinematic factor, and this depends on the polarizations and the moment of the external gravitons. Okay, this is a well-known factor, but I'll not write down the expression because it's somewhat complicated. So only thing, let me say that it carries 8 powers of momentum. So here is that formula again. Now this term, the first term, 64 over STU, this is a supergravity contribution. And this is S duality invariant by itself, okay, which is not surprising because supergravity action is S duality invariant. The second term is not S duality invariant, but there is an S duality invariant completion containing one loop and non-perturbative terms. This was postulated first by Green and Gutperle, and by now there is enough evidence for this. So they wrote it in terms of non-holomorphic Eisenstein series. But what I have done here is to give the weak coupling expansion of this whole function. So the leading term is 2 zeta 3, that's this one. This is the one loop term. And then it contains a series of non-perturbative terms, okay, which look quite complicated. So here e to the 2 pi tau is A plus I over GS. So A is the vacuum expression for the Ramond-Ramond scalar. GS I have already introduced as string coupling. And e to the 2 pi I k tau, these terms are contributions from k D-instantons. And e to the minus 2 pi I k tau star are the contribution from k anti D-instantons. And here you see a whole series expansion in GS. These are corrections on top of a given instanton. Okay, so there's a power series expansion in GS for each instanton. So from this, we can get the following prediction for the leading term in the k D-instanton contribution to the 4 graviton amplitude. So here I have re-expressed kappa in terms of GS. Okay, so you don't see any kappa anymore, but you have this GS to the 7 by 2. There is a complicated factor, okay, over here. And everything else is already given earlier. So our goal in this talk will be to reproduce this from direct D-instanton computation, okay, without using S duality. And in fact, once this is done, one can show that all the higher order terms in the power series expansion in GS can be obtained using the differential equation implied by supersymmetry. So supersymmetry is powerful enough that if we give the leading term in the D-instanton contribution, it generates the whole series, in fact, the whole function. So this means that if we are willing to use supersymmetry, then knowing these, once you have derived these, that determines the function completely without help of S duality. Nevertheless, it's important to develop techniques for evaluating the higher order terms by direct perturbative computation, because as I said, the purpose of this analysis is not to just verify known results, but to develop techniques that can be applied to cases where there is no S duality or the supersymmetry is not powerful enough. And this, in fact, is work in progress by the Harvard group. And as I stated, they also determined the G-string dependence of the K of the single instanton term of this earlier. So here is the same expression again. So in this expression, this term, e to the 2 pi I k times e to the minus 2 pi I k by GS, this comes from exponential of the action of k instantons. And we will not discuss this term any further. Okay, that's the standard term. Okay, because k instanton contribution will be given by, we'll have an accompanying term e to the minus k times the instanton action. Okay, and that's what this is representing. So our goal will be to reproduce the rest of the terms, okay, that we see in this expression. So let me now begin the single instanton contribution. So the leading contribution here comes from the product of 4 disk 1-point functions and arbitrary number of annulus 0-point functions. So the general rule for D-instanton computation is that you just try to maximize the number of disks because each disk gives you 1 over GS. Okay, so that's why you have the 4 disk amplitudes. And because the annulus doesn't have any factor of GS, it has Euler character 0, you have to resum, you have to exponentiate it because you can insert as many annuli as you like. Okay, so that's what this exponential of the annulus represents. So we'll define n as I times the exponential of the annulus diagram. And our first task will be to basically calculate n. In fact, at this order, all the subtleties reside in the calculation of n, because these come from standard worksheet calculations. Okay, somewhat tedious, but straightforward. So we'll be focusing mainly on this computation. And the one thing I want to point out here is that we include disconnected worksheet because individual worksheets do not conserve momentum. D-instanton breaks space-time transition invariance. And the momentum conservation is restored at the end after integration over 0 modes. And we'll see later how that is done. Okay? But because there is no momentum conservation on individual worksheet components, you have to include disconnected worksheet. Okay, so here is the expression again. Now for type 2b D-instantons, A is known. Okay, here is the expression given in terms of the Jacobi theta functions. This in fact is 0, but I have written it for symmetry. And in fact, there is a theta function identity that says that A is identically 0. Okay, these terms all cancel. So this is the result of cancellation between the Nebuchadnezzar sector and the Ramond sector of the open string states. The first 2 terms come from the NS sector and the last 2 terms come from the Ramond sector. Now, if this was the whole story, then you could just stop here. Okay, the price you pay is that you don't get anywhere close to the answer that you saw earlier, which was predicted by Green and Goodward. Okay, so you have to understand what this formula means. So to do that, we have to look at the general structure of A. Okay, and this in fact is the general form of A. L0 is the standard Virasoro generator. Okay, for the open string. Okay, this is the worksheet formula number. Sorry, this is the space-time formula number of the state. Okay, worksheet for the JSO projection is already understood inside the trace. So the fact that A vanishes shows that the contribution from positive L0 states cancel in both Fermi pair. Okay, that's a consequence of supersymmetry. And for these, in fact, there are no subtleties and the cancellation is genuine. It's not necessary. In more general cases, this cancellation may not happen, but here it does happen, and that's genuine. But this cancellation that is so cannot be trusted for the 0 modes, and we need to treat them carefully. And to do that, it will be first useful to regulate the system by introducing a non-zero value, non-zero L0 value, H, for the 0 modes at the intermediate steps. And we need to do it preserving BRST invariance and conformal invariance. And the easiest way to do this is to put slightly shifted boundary condition on the 2 boundaries of the annulus. And this gives a contribution to L0, okay, that we'll use to regulate. This preserves conformal and BRST invariance on the worksheet. So there is no problem in dealing with this regulation. So in the regulated system, A is given by this. Okay, it's still 0, of course. And now I'm going to do a series of manipulations which look crazy at the beginning. Okay, but its meaning will become clear later. So first, I'm going to write this 8 as 10 minus 2, okay, which is an identity. Then I'm going to do these integrals over t. And this can be done here and write this as, so this gives logarithmic terms, and because you are exponentiating, you get the ratios. Now here, I should point out one important aspect of this formula. The ability to do this, integral and get a ratios of h's of this form relies on the fact that this integral doesn't have ultraviolet divergence. Okay, that this is, there is absence of UV divergence as t goes to 0. That's at UV point. Okay. Now this, the fact that these cancel exactly, that's a consequence of supersymmetry. That may or may not happen in a generic case. But the fact that as t goes to 0, this contribution, okay, goes to 0, so that the integral is finite from t goes to 0 limit. That's the magic of string theory. Okay, that happens in any string theory where there's a closed string tachyon. So that's the important point you should remember. Okay, so this, so even though many things simplify by supersymmetry, the main thing that we need is not supersymmetry but absence of closed string tachyons, and that's what is needed to go from here to here. Okay, the next step is to rewrite this as a set of integrals, okay, which I have written here. This in fact is an identity. Okay, so you see that nothing has changed. N would have been I because A is 0, it's still I, okay, because these things cancel, and we can show that this integral I gives you identically this. So here xi mu are the 10 Grassmann even modes which are related to D-instanton position. PQ are 2 Grassmann odd modes which represent ghosts. And chi alpha are 16 Grassmann odd modes which represent fermion zero modes. G alpha beta here is an antisymmetric 16 by 16 Hermitian matrix that satisfies the G square is H times the identity matrix. And as I said, the equality of this and this is an identity. Okay, everything can be done explicitly here. So after you do these integrals, you recover exactly this. For example, the xi mu integrals gives you the 1 over h to the 10 square root. The integral over PQ produces this h, okay, which is square root of h square. And integral over the chi alphas produces this square root of h to the 8. Okay, so now we proceed as follows. I'll give the steps and then I'll give the final result. So the first task will be to interpret n as Siegel gauge fixed path integral of open string field theory on the instanton. And this fixes the normalization of the integration measure. Okay, a priori, the open string field theory doesn't have a fixed integration measure. That's arbitrary. Okay. But when we try to interpret n, okay, which is given here, okay, as the Siegel gauge fixed path integral of open string field theory, okay, that fixes the normalization of the integration measure in string field theory. So in this interpretation, the modes P and Q represent Fourier-Popov ghosts in the NS sector. Then you show that the Siegel gauge becomes singular as h goes to 0. Okay. And this in fact is the reason why the coefficient of the PQ term that represents the ghost kinetic operator vanishes. Okay. And it's clear that when the ghost kinetic operator vanishes, the gauge choice is singular. Right? And so once we identify PQ as the ghosts, okay, then the fact that here the coefficient of PQ is h, which goes to 0 as h goes to 0, clearly indicates that the gauge choice is breaking down. So the remedy will be to work with the original gauge invariant path integral before gauge fixing. And this will get rid of the modes P and Q from the integral, but it will also introduce some additional variables on which you have to integrate. Okay. So in the next slide, I'll write down the final result, okay, and I'll at least try to motivate how that comes. So here is the final result after setting h equal to 0. This I was there, it's still there. These integrals we see, okay, as they were before. As h goes to 0, the xi and chi alpha dependence all goes away because the matrix G alpha beta becomes 0, h is 0, so there's no kind of quadratic term involving the xi mu. But you see a new mode has appeared, new mode phi. So what is phi? Phi is the mode that was wrongly fixed to 0 in the Siegel gauge. Okay, so that has come back. And theta is a gauge transformation parameter that was used for the wrong gauge fixing.
Ashok,
So in fact, for non-zero h, if you start with this, and if you carry out Fourier-Popov procedure, you will find that it exactly reproduces the integral that we had earlier.
Ashok, you have 5 minutes time.
Thank you very much. Okay, so now we can do the phi integral. Okay, that's the easy part. That's the simple Gaussian. And we get a factor of 2 root pi. Okay, and now we have to understand what these integrals are. So the xi mu's, I have already said that they are related to the location of the instanton in space-time. Okay. But now we have to be more precise. We have to understand what exactly is the relation between xi mu's and the x mu's. And the precise relation may be found by comparing these two things. that first we can look at the explicit coupling of xi mu to a string amplitude, and this you do from worksheet computation. And you compare that with the expected coupling of x mu to a string amplitude, because the dependence on x mu should be of the form to the ip dot x, because x is the D-instanton position. P is the total momentum carried by all the closed string vortex operators. So by doing this comparison, one finds this relation between xi and x. GO here is an open string coupling, which is related to the closed string coupling GS by the specific relation. And this means that the product over xi mu, d xi mu, I can now rewrite as product over dx mu with this extra factor over here. The next thing is to understand the gauge transformation parameter theta, right, which appeared in the denominator. So what is this? So this turns out to be related to the rigid U1 gauge transformation parameter alpha on the D-instanton. So let me explain what this rigid U1 gauge transformation is. So if we take an open string that connects the D-instanton to a neighboring instanton, okay, this is some spectator, there is a U1 symmetry under which this state picks up a phase of into the I alpha. Okay, so this is a standard U1 that is there on every D-brane, including D-instanton, even though there is no dynamical gauge field on the D-instanton. So we compare the infinitesimal transformation by alpha to the string field theory gauge transformation parameter generated by theta. Okay, take any state of the open string and compare these two gauge transformations. By doing this comparison, you find the relation between theta and alpha. Okay, and this is the relation. So integral d theta we can rewrite as now integral d alpha. Okay, with this factor. And now you see from this definition of alpha that alpha has period 2 pi, because 2 pi rotation doesn't do anything. Okay. So this integral gives you 2 pi. So this theta integral gives you 4 pi by GO. So this is what goes in the denominator. So after doing all that, this is the final expression for n that we get. These are now the instanton positions. The chi alphas are the zero modes on the instanton, the fermion zero modes that are associated with broken supersymmetry. So the x mu integrals eventually generate the momentum conserving delta function that I said was missing initially. And the integration over the Grassmann odd variables, chi alpha, they will vanish unless there are 16 insertions of chi alpha in the rest of the amplitude. Okay, so you need to bring down 16 factors of chi alpha from somewhere. Okay, and this has to be done from the rest of the amplitudes. And in fact, one can do a simple analysis and show that of these 4 disks, the only non-vanishing contribution comes from inserting 4 fermion zero modes on each of the 4 disks. Okay. So a disk without any fermion zero mode or a disk with 2 fermion zero modes give identically 0 result. So you need at least 4 fermion zero modes on the disk with a Graviton insertion to get a non-zero result. So the distribution is unique. Okay. So now the chi alpha integral gives a factor of epsilon. Okay, this 16-dimensional epsilon symbol. This multiplies the product of 4 disk amplitudes with these fermion zero mode insertions. This is standard worksheet calculation. Okay. And at the end of all this, and after you put in all these factors over here, okay, we precisely reproduce the Green-Kuthberg prediction for k equal to 1. So this is the result for single D-instanton. So I'll just take 2 minutes to finish the rest. So k instantons. So for k instantons, the center of mass degrees of freedom give the same integral as a single instanton, except for some powers of k from Chan-Paton factors. Okay, so that is trivial. The relative degrees of freedom, okay, which is the SUK part, they have to be analyzed similarly by gauge unfixing the Siegel gauge, because the worksheet calculation always gives the result in the Siegel gauge. So you have to gauge unfix. And then you have to explicitly integrate over the out of Siegel gauge modes. And the remaining part is a supersymmetric matrix integral, which in fact had already been computed in the 90s, late 90s, while studying the index of multiple D0 branes. Okay, and in fact, these are the 2 groups which did this computation. So you simply have to take their result and put them together. Okay. And putting these results together, you will produce precisely the leading term in the k instanton amplitude as predicted by Green and Kuthberg. Okay. And as I have said earlier, that once you have the leading term, and if you are willing to use supersymmetry, then you generate the whole function. So final slide, conclusion. So what we see from here is that string field theory gives a systematic procedure for computing D-instanton contribution to the amplitudes. So we should be able to apply this procedure to calculate D-instanton contribution in situations where SDLP may not be of help. For example, in semi-realistic string compactifications, other problems where D-instanton corrections might play a dominant role, and perhaps also to find a non-quadratic definition of string theory by summing over saddle points, as I mentioned earlier. Thank you.
Oh. Actually, I had the question, Ashok.
Okay.
So to use supersymmetry to get higher genus corrections, if it was just linearized supersymmetry, then it would not tell you anything about higher GS corrections. Is that correct?
No, you do. I mean, you get, because you get a second order differential equation, right? Linearized supersymmetry. So once you have the second order differential equation, okay, that was a partial differential equation, but in a given instanton sector, it's just ordinary differential equations, second order ordinary differential equation. And now the leading term fixes everything, the whole function.
Okay.
So this is really linearized supersymmetry.
But linearized supersymmetry would not affect the coupling constant, right?
It does somehow. I mean, the point is because it's a derivative with respect to tau, right?
Okay. Yeah, I guess when I mean linearize, you linearize around tau being non-zero. I was going to linearize around GS equals 0. You're somehow linearizing around something else. Is that right?
Yeah, exactly. The linearize around some fixed tau.
Okay.
Which could be coupling.
Okay, thanks.
Rasi, please. Rasi, can you hear?
Oh, me, sorry. So I have a simple question. So why are D-instanton enough to compute non-perturbative contribution to the 4-point amplitude? Is there a supersymmetric explanation?
Okay, so the point is that typically what happens is that if you get the, in any given topological sector, if you have the leading saddle point, then typically resurgence fixes everything else. Okay, here of course there is a lot of power from supersymmetry. But even if you didn't have supersymmetry, right, I think just for at least in type 2b in 10 dimensions, I think the only topologically non-trivial sectors are coming from D-instantons. Ines fibrin instanton, for example, doesn't have a contribution in 10 dimensions, right? They come only after the compactify, so that they wrap and give cycles. So here, I think the only topologically non-trivial instantons are D-instantons.
So do you believe that this works even for non-supersymmetric quantities?
Yeah, this procedure will definitely work. I mean, whether the supersymmetry may not help in generating the higher order terms from the lowest order. But if you want to do a systematic worldsheet computation, then there is nothing about supersymmetry that you have really used in this procedure.
Okay, thank you.
Oliver, please.
Yeah, suppose I want to apply this method for higher derivative operators in type 2b, say d to the rth, d to the 8, r to the 4th, and beyond. What are the main problems and perspectives to get the high derivative instanton contributions?
I think there is no technical difficulty. Okay, there is no conceptual difficulty. The difficulty may be more technical, that to get the higher derivative terms, I think if you just look at the product of disk amplitudes, that's not what is going to give the higher derivative terms. You need disk, you have to insert higher point functions on the disk. But the normalization, once you have computed the normalization for k D-instanton, that is fixed. There is nothing, the normalization, you don't have to compute anymore. Right? So the problems are more technical, that you have to do the worldsheet computation appropriately. In fact, if you ask for the supersymmetric ones, d to the 4, r to the 4, and d to the 6, r to the 4, these computations, so the Harvard group, I think C is on the line, so he can confirm. As far as the Harvard group, they computed the ratio of the d to the 4, r to the 4, and d to the 6, r to the 4 to the r to the 4 term. and that ratio comes out correctly. So once you know a normalization works correctly for the R to the 4, right, at least for single instanton, you also know the normalization works, the result is correct, right? The leading result is correct for the D to the 4, R to the 4, and D to the 6, R to the 4 terms.
So that means the path is clear for the Harvard group to go for 8 derivatives and more.
Well, maybe I think C is on the line, so he can clarify, perhaps.
Yes. I mean, I mean, you know, it's still work in progress, but we think we have already gotten the higher derivative order 1-instanton contribution coefficient correctly, but we actually currently have some, well, earlier we did a calculation based on a naive Ashoke worksheet calculation, and where there was some slight puzzle associated with that, and we're trying to do that properly using open plus string field theory, which we hope to resolve the puzzle, but that's still not finished.
And that's great news. Really looking forward to
the
that.
puzzle, as far as I understand, C is only about the higher order terms in the R to the 4, right? For D to the 4, R to the 4, and
it was for all SPU dependent, but at 1-instanton order at the first leading order in GS.
yes, okay.
Yeah, but you know, there's arbitrary momentum dependence. So not just at the R to the 4th order.
I see.
Okay.
Yeah,
Okay.
let me just speak up, Frans Klinkhamer. So you look at instanton, anti-instanton, but from the work on quantum field theory from many, many years ago, we also know that there may be non-trivial contributions in the topological charge 0 sector, right? So you can view that roughly as a bound instanton, anti-instanton. And then roughly it would have twice the action, right? Minus the binding effect. Have you looked at that?
Yeah, so in this case, we know from the supersymmetry argument that there is no such contribution for R to the 4th term, because the differential equation that I alluded to fixes the non-zero results to come only from the tree level and 1 loop. Otherwise, hard genus contributions just simply don't satisfy the differential equation. Mm-hmm. So in the 0-instanton sector, at least for R to the 4, we know that there is no other contribution using supersymmetry, not using direct instanton calculation. But we also know that D to the 6 R to the 4 does have instanton anti-instanton contribution. And that will be a challenging thing to do. I mean, in principle, one should be able to get those from these kinds of calculations, but that has not been done certainly.
Okay.
Okay, the last question from the Princeton node, please.
I guess this is us. So I have 2 questions. First, kind of follow up on the previous question. In cases which are not supersymmetric, there are high order corrections, which usually make the instanton contribution ambiguous because it's contaminated by the high order contribution in the power series expansion. So in what sense is this computation meaningful in non-supersymmetric situations? And the second question is whether you have a physical interpretation of the split by H of the 2 boundary conditions that you used.
Okay, so the second question maybe I can answer first. The split by H is essentially that instead of talking, doing the calculation for open string with both ends on a single D-instanton, you are thinking of this as open strings with both ends, the 2 ends lying on 2 different D-instantons. But when they coincide, the spectrum is identical to that of a single D-instanton. And that's the regulator that we are using. Okay, they think of this as open string not on a single D-instanton, but between 2 D-instantons. Okay, about this first question, okay, of course, I don't know the answer fully, but my understanding is that if we, in every topological sector, okay, so the D-instanton contribution is in a separate topological sector, okay, because you have this e to the 2 pi I k tau. So I think if we are looking for contributions of the form e to the 2 pi I k tau, then there is no contribution of that kind from perturbative saddle points. Okay, you can get as high order as you want. They will give terms which don't have e to the 2 pi I k tau. So this instanton expansion, I think, does give the correct capture correctly the series expansion with the leading series expansion of terms which go as e to the 2 pi I k tau. So it's basically the axion which is important, 2 pi I k tau 1. That kind of contribution will not come from resumming perturbation series. It's like a theta term, right?
Okay, now we are over time. People who have more questions can leave it for the discussion session, which is going to start in a few minutes. Okay.